In this video, we are going to introduce the concept of isomorphism by asking the question, when are two rings really the same ring? So we're going to do this by looking at their addition and multiplication tables and what those tell us about the ring structure of a particular ring. We'll show how to make a ring look different without changing its structure, and then we'll describe what it means for two rings to be isomorphic. And this will be an informal definition. We'll give a formal definition in the next video. All right, so I want you to look at the addition and multiplication tables for P2. And remember, P2 is just the power set of a set with two elements in it. And you don't have to really remember what the rules are for doing addition and multiplication if you just look at this addition and multiplication tables. You can figure out everything just from there. So the question is, what is some information that you can get from the tables, even if you don't really even understand how multiplication and addition work in the power set? Well, first of all, you can tell just by looking at it that the empty set is the additive identity. How do you know? Well, if you look at the first row and the first column of the addition table, you can see that the empty set leaves everything alone. Empty set plus empty set equals empty set. Empty set plus the set containing 1 is equal to set containing 1, etc. Look at that first row. They all match what's right above them. And if you look at that first column, they match the element that's right across from them. And that tells us that empty set is the additive identity. Again, just from the addition table. You can also tell that every element is its own additive inverse. Now that we know what the additive identity is, we can look at what the additive inverses are. So, for instance, if you look where there's an empty set inside the multiplication table or the addition table, you can see what the additive inverses are. So, for instance, there is an empty set right across from 1 and right below 1. And that says that the set containing 1 plus the set containing 1 equals the empty set, and so they're additive inverses. And similarly, you can see that for all the other elements as well. You can see that the set containing 1 and 2 is a multiplicative identity. If you shift over to the multiplication table and look at the last row and the last column of the multiplication table, you can see that the set containing 1 and 2 leaves everybody alone with multiplication. In that last row, every element above that row matches what's in that row. And similarly with the last column. So let's look at another ring. Now, if you just look at this ring from a superficial point of view, this looks like a completely different ring. It has completely different elements. It doesn't have any sets in it. It just has letters, and then it has this addition multiplication table involving these letters. Here's the question though. Are these two rings really different? Well, if you do something clever like replace the empty set with A, and replace the set containing 1 with B, and replace the set containing 2 with C, and finally replacing the set containing 1, 2 with D, everywhere you see them in the addition and multiplication tables, it will look identical. Now, you should try it just to make sure that I'm not lying to you, but it is absolutely true. So this is a situation where we have two rings that are technically different because they have different elements in them, but they're basically the same because up to changing their names, they have the exact same addition and multiplication tables. When this happens, we call the rings isomorphic. And a good model for this is what I call the name change model. Two rings R and S are isomorphic if they have the same addition and multiplication tables if all you do is change the names of the elements. And an isomorphism is a function that tells you how that name change works. It tells us what the name of each element was changed to. And the way it does it is, if you take an element x in the ring R, then phi of x is going to be what the name was changed to. So x is the element in R, phi of x is the element in S that's playing the same role in S that x plays in R. So if we look at the set S equals A, B, C, D, and that's the ring with the addition and multiplication tables that I showed you a couple slides back, then we can define an isomorphism between the power set with two elements and S. And remember, in order to get the same multiplication and addition tables, we replaced the empty set with A, so phi of the empty set is equal to A. we replace the set containing 1 with the element b, so phi of the set containing 1 is equal to b. We replace the set containing 2 with c, so phi of the set containing 2 is also equal to c. And similarly, phi of the set containing 1 and 2 is equal to d. So when we do that, that phi is then going to be an isomorphism. So now see if you can apply some of these ideas on the activities. The name of the PDF file is called Introduction to Isomorphism.